All right, guys, this one's going to require some work. The beam is slanted in this case, so you're going to see how we're going to have to modify this problem to work it in our favor. This is the rod here from A to B. They want us to find the force in the cable, B to C, okay? So there's tension in this cable from B to C. It's angled at 60 degrees. The mass of the rod weighs 40 kilograms. So you're going to have weight, just mg, right? Multiplied by gravity, you get weight. You always start these problems off with the free body diagram. Okay, so let's do that. If you see here, we have from A to B, right? The rod itself, weight coming down, and weight I calculated for you guys is weight is equal to mass times gravity. And it's in newtons. We're dealing with SI units. And then look at what we have. Let's look at the system the way it is right now, right? You have force of A, it's a collar. So a collar only prevents movement in the positive X, and I mean in the X direction, right? It could slide up and down, so you're good on that piece. There's no reaction in the Y. It's just FA, in this case in the positive X, right? Or this is our coordinate system. On this one, you have a roller, okay, at B. So you only have a reaction in the Y, right? Because it could roll in the X direction. So you only have a force B pushing up. You have tension in the cable that we just said. You have the weight of the mass weight of the rod pushing straight down. So we have to characterize, before we continue, let's kind of look at it, okay? Let's use our engineering minds for a second. We want to find T. That's the ultimate goal, okay? Just by looking at the system, this is our X and Y. Just by looking at it in this format, and you'll see what I mean by format because we're going to change it up. I see that FA has to equal T, and I see that W has to equal FB. So these two are equal to each other, and these two are equal to each other. So just like that, I already know what FB is. It's going to be W, right? This is going to be 392.4 newtons pushing up. Now, I want to find T. If I do some of the forces in the X, FA is equal to T. Okay, I don't know FA, I don't know T. Let's do some of the forces in the Y. Some of the forces in the Y is W is equal to FB, right? This is coming down, this is going up. There's no other Y force acting, so they're equal to each other. So using these two numbers, it still doesn't give me anything regarding these two. So I don't know FA or T. So we're kind of stuck, right? Now, this is what we're gonna do. Just by looking at it, I wanna take a moment about this point, A. Well, why? Because I know W. I could get the component in this direction, right? Because this is slanted. So that means our coordinate system is like this, and it's gonna go like this, okay? That's 60 degrees, pushed everything up. So it was like this. Red is, the pink pencil is Y direction, blue is X. It shifted 60 degrees. The blue shifted 60 degrees. So now I want all of the forces in the pink pencil direction. I want weight in this direction. I want force of B in this direction. I want T in this direction, okay? That's what is gonna mess up our day, okay, just FYI. So starting at, this is what I did. I started at step 2. Step 2 is zoom in at this node right here, okay? So if you zoom in right at the center of the bar, we know the mass of the rod, the center weight, the center of gravity is at the middle, right? Assuming the geometry is all equal, which it is, you assume the weight it's right at the center, okay? So it's pushing straight down. So look, that's what I have here, that W pushing straight down. I have to get to the tail of the vector, which is a big circle right here, down to the head of the vector right here, right, for W, using this coordinate system, the one that got shifted 60 degrees. I want to use either this path and this path to get from the tail to the head of the vector. I don't want to go this way, because I want to get this like that, right? Okay, I want to get that path for the vectors because I want this perfect arrow to later do a moment about A to get the values, okay? Because that's what's producing that moment about A. So in this case, what I did was I labeled it x1 traveled this way, and this way, right? You could have done this way, it's the same thing, right? This one's still going in this direction, just like x2. I labeled x2 and x1. X2 would go this way, x1 would go that way. And I know that's 30. Why do I know that's 30? Because look, that's just a triangle right here. Boom, 60 degrees, there's a 90 degree, this should be a 30 degrees right there. And it kind of makes sense, right? Look, if this is, again, pink is our y, blue is our x, it shifted 60 degrees, so it went this way. Blue went 60 degrees, okay? Now, look at the pink one, okay? This is how it was right now. I'm sorry, still look at the blue one. If you look at the blue one, this went 60 degrees. So this angle right here, it was like that, right? From here to the blue is a 60-degree angle. So that means from here going straight down to the blue is a 30-degree angle. That's all it is, okay? But you can also see it from here, right? 60 plus 30 plus 90 is 180 for a triangle. And now that I have that, I'm going to solve for these two distances in terms of W, okay? Because I already know W, and I already know the angles, so I'll be able to get some numbers. In this case, sine 30 will give me x2 over W, right? Sine is equal to opposite over hypotenuse, boom. And then I solve for x2, W sine 30, okay? Then now let's do x1. Cosine 30 is equal to x1 over hypotenuse, right? SOHCAHTOA, cosine adjacent over hypotenuse, x1 over W. So I move W to that side and I solve for x1. x1 is equal to W cosine 30. Now I characterize W. I'm going to do the same thing for T and for FB, okay? In this case, I do T next. So if I do T next, check it out. Zoom in at T now, okay? Well, T's right here, that circle that you see here. And it's going this way, right? That's what we're looking at. We know this angle is 60 degrees. So again, remember, we want this coordinate system, right? T's going this way, straight to the left. We want to use this path and this path to get to T. From tail of the vector to the head of the vector. So you go this way. And you do the same logic that I did here, right? You know this angle is 60 because that's what they gave you. Sine is opposite, so it's y2 over t, right? Opposite over hypotenuse. And then adjacent over hypotenuse, y1 over t. Yeah, I'm just repeating the same steps. So now I'm able to get y2 and y1, okay? T sine 60, T cosine 60. Now, let's go to the next step, right? Do the same thing for FB now, okay? So FB, you want to break this up into two components. It's going straight up. That's what you see here. Now I'm zoomed in, okay? Straight up. I want to use this system, not this one, because it was tilted 60. And I want to get from the tail of FB to the head of FB. Tail of the vector to the head of the vector, using only this path. So I'm going to go this way, Z1, that's what you're looking at. I'm going to go this way, then I'm going to go Z2. And just like that, same process, right? Nothing different. I'm just going to go ahead and solve for Z1 and Z2, these lengths, right? These magnitudes of forces, not really lengths. And then I get this. So I'm using sine 30, or you could use sine 60, whatever. It's just going to change these numbers a little bit. But you get Z1 is equal to FB cosine 30, Z1 over FB, right? That's what we got here. And then Z2 is just FB sine 30, okay? So I hope that made sense. Just look at it. And that really is just the trick to this problem, okay? So now that I have all these, I can make a whole new free body diagram. And this is what I did here. So look at it. Same beam, right? FA didn't change. I didn't do anything with it. I characterized the 3 meters into 1.5 and 1.5 just for simplicity. W sine 30 was coming this way, remember? Look at W. We're here. This is W, right? The middle of the beam. Look at here. I'm using this length, the one coming down this way. And that was x2, W sine 30. Now, there should also be a vector pointing this way, pointing away from FA, right? Away from this, going this way. But I don't care about that. Why? Because it's not going to produce a moment about point A. It's going through the beam, okay? Now, I mean, you can still write it down, right? Because technically, W is coming straight down here, so that means it should have this component and that component. But I just didn't throw it in there, just so you guys could see it better. Same thing for t, right? I'm only concerned about this vector. So if I'm only concerned about that one, I'm looking at the y2, right? Zoom in at t, remember? This is t. I want this force. So that's y2, t sine 60. Boom, I just threw it in there. This one is this one, z2. That one is fb sine 30. So I just threw it in there. Remember, z1 is going through the beam. It's not gonna produce any moment. And you might be thinking, well, yeah, no, actually, it is, right? Because if you start it here, you're going this way, it's producing some distance to FA. That's not how it works. It's pointing into the node, and the other one's also pointing into the node, okay? So think of it that way. This is just so you guys can visualize it. But now that we have our new free body diagram, you could use either or at this point. You could use this one for some of the forces in the x and y, right? FA is equal to t, W is equal to FB. And then you use this one for the moment. So that is what I did here. Let me kind of cover this one up like that. So some of the forces in the x and y are equal to 0. So that's what I told you guys. FA is equal to t, W is equal to FB, which is equal to 392.4, remember, right? So now let's go to the last step. I'll just show you guys some of the moments about A. Now I'm going to use this diagram to take the moment about this point. So this one's going to produce a negative moment because it's going clockwise about this point. It's W sine 30 times 1.5. Negative W sine 30 times 1.5. This one is doing FB sine 30 times 3 is doing a positive moment about this point. So FB sine 30 times 3. T sine 60 times 3 is doing a clockwise moment. So that's a negative T sine 60 times 3. Plug in your numbers. We found weight. We know FB. FB and W are the same. We're looking for T, and boom, that's your answer. Just look at it for a second. That's just math at that point. But it really is that simple, guys. This method is the whole point of these 3 steps right here, 2, 3, and 4, is to characterize these forces in the forces that we want, okay? Now doing that, everything's in this direction. You could just take a moment about it, and it'll give you the answer like we just proved it. So I hope that helped. Let me know if you didn't. Any questions, just comment, and I'll answer, and we'll go from there. Cool, thank you.